Hi everyone, this is a quick video lesson to discuss Eulerian graphs. So first we need to get a little bit of terminology under control here. We have these different phrases, a walk, a trail or a path, which is just a way of moving around a network. I have an example of a network shown here. And we classify these things according to whether we go along edges more than once or whether we visit vertices more than once. If we start and finish at the same vertex, we describe this as closed, so a closed trail or a closed path, for example. And if we start and finish at different vertices, we call this open. Now let's do a couple of examples and see what we're talking about here. So, for instance, if we went along the from P, T, S, T, R. So we need to ask ourselves the following questions. Have we repeated any edges? Well, let's just see what we've got here. We go from P to T to S, back to T, and then to R, over there. I think we can see we repeated this edge. So repeated edges, that's a yes to that one. Have we visited the same vertex more than once? Yes, we visited vertex T, we went through T, and then we went back to T, so that's a yes. Did we start and finish at the same place? That's a no. So let's go up to our little table here and we'll decide. Are repeated edges permitted in a path? No. In a trail? No. So the only way we could have repeated edges permitted is if this was a walk. And we're also allowed to have repeated vertices. Now, we did not start and finish at the same place. This is an open walk. That's the first one. Let's clear that up a little bit and we'll try a different one. Let's imagine we went SQR TP. Let's trace this one out. So we go from S to Q, down to R, across to T, and then we go to P. So, have we repeated any edges? That's a no. Have we repeated any vertices? That's a no. And was the start equal to the finish? That's a no. So we have no repeated edges, could be a trail or a path, but we have no repeated vertices. It's a path, and it is an open path. There we are. Let's try one more. Let's go STPQS. S to T to P to Q and back to S. Have we repeated edges? No. Have we repeated vertices? Now I know you're going to be saying that that's a repeated vertex, but that one doesn't count. If the beginning and the ending vertex are the same, then that comes in here under the business about being a closed route, whatever we classify it as. So we don't count that as a repetition if the first and the last one. Did we finish and start at the same place? Yes. So it is a path because there's no repetition. It is closed. Now, in the case where we have a closed path, we call that a cycle. There we go. Whenever you have to classify movement around a network as a walk, a trail, a path, always ask yourself these three questions. Have you repeated edges? Have you repeated vertices? And did you start and finish at the same place? Then you'll be able to decide. Most commonly, yeah, you do have to know them all, most commonly we'll be dealing with trails, and in the case when the trail is closed, we'll be calling it a circuit. And that leads me down to the next section. Let's consider this graph. Now, Euler wanted to know can we use a trail or a circuit that includes every single edge? So for this to be Eulerian, we must use every edge. Now let's see if we can make an Eulerian circuit or an Eulerian trail. Remember, no repetition of edges, repetition of vertices is okay. So let's just see what we can do here. We could start here, we could run down there, we could go across here, we could come up there, everything's going great, we could go up here, and now we have a problem. If I turn left, I go down to P, and then I'm stuck with nowhere else to return, and if I go down to R, I'm also stuck. So I cannot cover all of the edges without repeating myself. If I went down here, I'd have to backtrack. No, not allowed. We don't want to backtrack and do edges twice to be Eulerian. That doesn't mean it's impossible. Let's try starting from a different vertex. Let's try from here. I could go along this. I could come down to here. I could go up to Q. Now it's all right to visit Q twice. I just haven't gone over the same edge. Then I can come down here, and there we go. I went over every single edge. I didn't repeat any edges. I did repeat a vertex. You would have noticed that I started here and I finished here. So this is a trail because it is an open, an Eulerian trail. Every edge was used. We need every single edge to be used if we want this to be Eulerian. And the word trail means what it did before, that we didn't repeat edges, we could repeat vertices if we wanted to. Now let's take a quick look at why that one worked when I started from Q. The degree of this vertex is 2, this is degree 2, this is degree 2, this one is degree 3, and this one is degree 3. Now, if you imagine travelling along an edge to a vertex, then to be Eulerian, I cannot backtrack, I can't go back. I have to have another edge to take me away from that vertex. So edges that are in pairs like that would work. I can enter by one edge and exit by another. And then somehow or other, maybe I have another edge coming back into here and then another one going out there. So 4 would be okay. I could perhaps have one coming in from this direction and going out in that direction. As long as I had an even degree, I'm going to be okay because I can transit through the vertex. It doesn't matter how many times I visit the vertex as long as I don't use the same edges twice. What about an odd number? What if I had a vertex that had an odd degree? So if there's my vertex, if I have a trail coming in and then a trail going out, I can transit through. But then if I have another one coming in, I get stuck there. So as long as I finished at that vertex, I'd be okay. Alternately, perhaps I would start at that vertex, move off, and then at some other time transit through the vertex on these other two. But really, that's about it. If I had odd degree, I either have to start or finish at the odd degree vertex. And that's why it worked when I started here. I started at an odd degree vertex. Now, I don't even have to do the same path. I can come down to here. I want to finish at this one. So I'm going to go up there, across there, and then down here. And I've finished at the other odd degree vertex. So an Eulerian trail belongs on a semi-Eulerian graph. And what do we know about that? There would be 2 vertices with an odd degree. Only 2. All the other vertices would have to have an even degree. And importantly, I would have to start and finish my Eulerian trail at the odd vertices. That's an Eulerian trail. They're fairly common. But more importantly would be an Eulerian circuit. These are probably a little bit less common. So what does an Eulerian circuit mean? Well, it's a bit like this. We must use every edge. We absolutely must. If we don't use every edge, it's just a regular circuit instead of an Eulerian circuit. Let's begin by writing the degree of every vertex. This one is degree 2, this one is 2, this one is 4, this one is 2, this one is 4, and this one is 4. So we're in luck. Every vertex has an even degree. That means we should be able to find an Eulerian circuit. Now it still could take a little bit of trial and error to do so. Let's see, I might start at A. Let's go to A, then let's go down to B, then to C, then back up here, then we can go down here, then we can go across there, then we can come down there, and then back up here, down there, and done. I did not retrace any edges twice. I did visit vertices more than once, that's allowed. But there we go. That's a little bit of network terminology. Up here, a walk, a trail, and a path. Like I said, when we're dealing with Eulerian graphs, we're really interested in trails and circuits. So repeated edges, no. Repeated vertices, possible. That's allowed. And if I had a semi-Eulerian graph, then I will have an Eulerian trail. Then this one with an Eulerian circuit, that's just called an Eulerian graph. But of course, it is possible to have graphs which neither of those apply, and they are called non-Eulerian graphs. All right, that's a very quick introduction. Don't forget to read your textbook and try some questions for yourself to reinforce these ideas. Thanks for watching.